In section 12.6, we're going to talk about tessellations. Repeating patterns actually play an important role in Native American art. Many times, actually, Native Americans use tessellations and repeating art in their rugs or clothing. So let's go over a few vocab words. A pattern that has translation symmetry. So a pattern would have translation symmetry if it can be translated along a vector so that the image coincides with the pre-image. A frieze pattern is a pattern that has translation symmetry along a line. So, two vocab words, translation symmetry and frieze pattern. Now another vocab word talks about glide reflection symmetry. Both of the frieze patterns shown below, so let's look at this. A frieze pattern is a pattern that has translation symmetry along a line. Both of the frieze patterns below have translation symmetry. A pattern on the right, which is over here, has glide reflection symmetry. A pattern with glide reflection symmetry coincides with its image after a glide reflection. So if you notice, if you take this little part here, if you slide it and then reflect it along this parallel line of symmetry, you'll notice that it is reflected. So we can slide and reflect. So therefore, this one on the right has glide reflection symmetry. So once again, translation symmetry is if you can take something and translate it along a vector, up, down, anywhere, so it coincides with the pre-image. Frieze pattern is a pattern that has translation symmetry along a line. And then glide reflection is when you can take the image, do glide reflection, and then it coincides with its image after their glide reflection. Now, I do not expect you to draw these patterns in any way, so do not think that you have to draw these. I do want you to write down the examples, but you don't need to actually draw the pictures because it would be too hard for you to do that. Now in example 1, I want you to identify the symmetry in each frieze pattern. So if you look at A, I do want you to write down 1A. You don't need to draw the picture, but it does have translation symmetry because I can take any of these little diamonds and slide them to give you another part of the pattern. Glide reflection is, could I slide any part of this and then reflect it to give you the same thing? Absolutely. You can reflect it down, you can reflect it across. No matter where I have, this has glide reflection symmetry. Now the one on the right is translation symmetry because I can slide any of these figures to the right or left. But I do not have glide reflection. You cannot slide and then reflect. If you reflect anything here, it is not symmetric. So A is translation symmetry and glide reflection symmetry. B is translation symmetry. Now, a tessellation, otherwise called tiling, is repeating a pattern that completely covers a plane with no gaps or overlaps. The measures of the angles that meet at each vertex must add up to 360. That's important. Each vertex, for example, you can see the colors here. The red plus the blue, the green, and the yellow, we make almost like a circle. It's a 360-degree measure after you add up all the angles. In the tessellation shown, each angle of the quadrilateral occurs once at each vertex. Because the angle measures of any quadrilateral add up to 360, any quadrilateral can be used to tessellate the plane. 4 copies of the quadrilateral meet at each vertex. So we have 1, 2, 3, 4 meeting at each vertex. In example 2, we're actually going to use transformations to create tessellations. So, in A, you can see we have a triangle. If we take the triangle and rotate the triangle 180 degrees about the midpoint of one side, look what I did. Take it, I rotate about the midpoint. Now I translate this exact figure to the right, and I make a row of triangles. Then I can translate the entire row, and I have made a tessellation. Now in part B, I have a quadrilateral. So once again, I rotate the quadrilateral 180 degrees about the midpoint. So look what I did here. Now you could have not rotated it to the right. You could have rotated it up and had the quadrilateral up here. So there are other ways to do it. But then I take this shape and I can make a row. Then I take the row and then I can translate the row up or down to give me a tessellation. So remember, when you're given a shape, you're going to first rotate the figure 180 degrees about any of the midpoints of one side. And that's going to give you a shape with two figures. You're then going to make a row out of it, and then you're going to take that row and then translate the row either up or down. Now, in the next set of vocab words, we have a regular tessellation. Just like a regular polygon has all congruent sides, a regular tessellation is formed by congruent regular polygons. A semi-regular tessellation is formed by two or more different regular polygons, with the same number of each polygon occurring in the same order. So, a regular tessellation uses the same shape, and it's regular, so all sides would be equal. In the semi-regular shape, you can take multiple regular polygons. So we have like a square, we have then two equilateral triangles. If we use them all equally in a reoccurring order at every vertex, so if you look at this vertex here, each vertex has a polygon occurring in the same order. So if you looked here, we have two blue triangles, two squares, and a green triangle. Every vertex is the same thing. Two blue, two yellow squares, and a green triangle. Every vertex here, and it says it right here, every vertex has two squares, three triangles in this order. Square, triangle, triangle, triangle. Square, triangle, triangle. It's a recurring pattern at each vertex. So this is a little hint, and this is found on page 865. Here's what this student says. When I need to decide if given figures can be used to tessellate a plane, I look at angle measures. To form a regular tessellation, the angle measures of a regular polygon must be a divisor of 360. To form a semi-regular tessellation, the angle measures around a vertex must add up to 360. For example, regular octagons and equilateral triangles cannot be used to make a semi-regular tessellation because no combination of 135 and 60 degrees would add up to exactly 360. So if you took both of these regular polygons and you used an angle of 60 degrees and 135, you cannot add those up in any way to give yourself a semi-regular tessellation. So let's look at example 3, A, B, and C. And I do want you to write the answers to these down. In A, is this a regular tessellation, a semi-regular tessellation, or neither? So if you look, first thing you'll look at is, are the shapes regular? So we can see these are all squares. They're all the same side, so therefore that works. And these look like octagons, and they're all regular. So we have two regular octagons and one square. Now we have to pick a vertex. This is important. Pick any vertex. What makes that vertex? Two octagons and a square. Any vertex you pick, two octagons and a square. Two octagons and a square. Two octagons and a square. Any vertex has two regular octagons and a square. Therefore, since they're different shapes, the tessellation is semi-regular. Now in B, we only have squares. Squares are regular because it's a regular quadrilateral. So the tessellation, since it's one regular shape, is regular. And the last one looks kind of like a rug. But if you look at it, we have multiple shapes in here. And here's what you need to look at. If you look at the vertex, and I know it's kind of hard to see, but if I pick, for example, this vertex right here, it looks like we have 6-sided shapes. And like here, we have two blue and two yellow. So we have four of the same shape. But here, we have two 6-sided figures, and we have a square. So therefore, this vertex does not have the same combination of polygons as the other vertex. So irregular hexagons are used in this tessellation, and it is neither regular or semi-regular. So you would say neither. In example 4, we're going to determine whether polygons will tessellate. So to determine whether a given regular polygon can be used to form a tessellation, remember that if we're using regular polygons, you have to determine if each angle is a divisor of 360. So if we look at A, we have a pentagon. A pentagon, if we find the interior angles, it's 108 degrees. 108 cannot divide into 360. Therefore, A cannot be made into a regular tessellation. Now, B, we have a square and we have an octagon. So the interior angle of an octagon is 135. A square is 90. So can any combination of 135 and 90 give you 360? And the answer is yes. You can have an octagon, and a square. So we would have two regular octagons and one square meeting at each vertex. So B would be an example of a tessellation, and they have an example here shown. So our vocabulary for this section would be translation symmetry, frieze pattern, glide reflection symmetry, tessellation, regular tessellation, and semi-regular tessellation.